Today I would like to talk about ferromagnetic materials. So we've already seen that if we place a material inside a magnetic field V, a magnetic field is produced inside the medium. So there is a field that exists inside vacuum created somehow. That field is mu naught H. Right? We know that. We know this. So if H is the magnetizing force, and if we're talking about fields, then we have to multiply with the mu naught to give it the dimensions of a field. So we place a medium inside this field, mu naught H. This medium develops magnetization, which is a property of the medium, and it depends upon how much is H. This magnetization is M. As a result of the magnetization and the external stimulus, which is mu naught H, a net field is produced inside the medium. That field is B. And this B is, as we've seen in the previous lecture, is a vector sum of mu naught H and mu naught M. So H and M have the same dimensions, and if you multiply each one of them with mu naught, we get the dimension of a field of Teslas. So a net field is produced inside the medium, which is a combination of the magnetization of the substance as well as the external stimulus, which is mu naught H. This mu naught H has been produced somehow by some external means, by some free currents, for example, flowing in the solenoid. Now this M depends upon H, and it's related to a constant called the susceptibility. This guy can be positive. It's positive for paramagnetic materials and for ferromagnets. For ferromagnets, it takes up a large value. For diamagnets, this guy is negative. So for paramagnets, chi is positive and it's really small. So of the order of 10 is power minus 4 to 10 is power minus 6 or 5 perhaps. For diamagnets, the generally occurring materials, this chi is negative. And again the absolute value is really small. It's of the order of 10 to the power minus 4 to 10 to the power minus 3 perhaps. For ferromagnets, chi is much larger, is positive, and it's big number. It can be in the thousands. For example, for an alloy such as mu metal, chi can approach 10 to the power 5. It's really large. So these were the constitutive relationships that we encountered in the previous lecture. So for ferromagnetic materials, we observed that if we were to plot the magnetization of this medium versus the applied field, first of all, chi depends upon H, which means that this relationship is nonlinear. And this is the kind of curve that we experimentally observe for different kinds of ferromagnetic materials. So it's non-linear, it's not a straight line. The slope of this line is different at different points, and the magnetization is really large. So if on the same scale I were to plot the magnetization of a conventional paramagnetic medium, the slope will be almost zero, and the magnetization will be orders of magnitude smaller than the magnetization of a ferromagnetic material. I can't do justice on the blackboard because there are a few orders of magnitude differences. Look at this value, it's 10 to the power plus 5. This is 10 to the power minus 4 or minus 6. So the difference is really large. Now what we would like to know is how do ferromagnets obtain this kind of loop? Why do we get such a loop for a ferromagnetic material? And what's the internal microstructure of ferromagnets? And why do I spend time on ferromagnets? Because they are ubiquitous. They make our wheels go. They make our civilization run. They generate electricity. They transmit electricity, notably. They make our automobiles run. There are generators and dynamos inside our automobiles. There are ferromagnets inside our hard disks. So memory is stored in ferromagnets. The millions of terabytes of data that we have floating around in the informational universe all owes its existence to ferromagnets. And that's why it's really important to understand how ferromagnets function. And why do they have a curve like this? And what's the internal structure of these ferromagnets? Now, generally, in common parlance, in conventional language, when we talk about a magnetic material, we are referring to ferromagnets. But remember that technically, all materials have some kind of magnetic property. They either qualify as ferromagnets, diamagnets, ferrimagnets, antiferromagnets, etc. Now, let's look at the concept of ferromagnetism in somewhat detail. Now, if I consider the element iron, iron is a ferromagnetic material. It's an element, and only 5 elements of the periodic table are ferromagnets. So iron has an electronic structure which goes as an argon core, and then it has 4s2 and 3d6. So it has 8 electrons outside the argon core. 2 electrons are in the 4s orbital, and there are 6 electrons in the 3d orbital. So if you look at the 3d orbital here, there are 5 kinds of d orbitals. We know that from our basic chemistry. And now we have 6 electrons that need to go inside the 3d orbitals. The 4s orbital, by the way, has 2 electrons. Alright? So the 4s electrons inside the iron atom, they are further away from the nucleus, and the 3d electrons are closer towards the nucleus. Let's look at the 4s orbital. The 4s orbital has 2 electrons, and then each electron has a spin. We know that, and it's a spin half particle. So each electron is a magnetic dipole. It's a tiny magnet on its own. An electron is a tiny dipole, it's a tiny magnet. It will produce a magnetic field. However, there are 2 electrons in the 4s orbital. So if I put 1 electron in here, and its arrow shows the direction of the dipole or the direction of the spin, then the second electron must also occupy the same orbital, but its spin is going to be opposite to the one that's already there. Now these 2 electrons that are in the same orbital have opposite spins. Now this is a consequence of a principle of quantum mechanics which is called Pauline's exclusion principle. So both of these electrons have opposite spins, and they are in the same physical location in the 4s orbital. So the net magnetic moment of these electrons is 0 because they have spins pointing in the opposite direction. So these electrons cannot render any magnetic properties to the iron atom, to an isolated iron atom. Okay? Now we have 6 electrons, and these 6 electrons have to go into these 5 subshells of the d orbital. So first of all, let's put in 5 electrons. Now the first 5 electrons go into different subshells. Why do they prefer first filling up the different subshells? Because they would like to go into different subshells. Each subshell is in a different physical location. For example, one of these subshells will have an electronic cloud structure like this. The other subshell will have an electronic cloud structure like this. And these cloud structures are just probability distributions of finding the electrons inside the particular orbitals. Now, if the electrons go into different subshells, they are in different physical locations on average. So they are further apart. And since electrons are all negatively charged particles, they would like to repel one another. So they would like to lower their energy by going further apart in different orbitals. And when they go in different orbitals, they keep the spins parallel. Okay? This is a consequence of a quantum mechanical principle, which is called. So the electrostatic repulsion between electrons makes the electrons go into different orbitals, into different subshells of the same orbital, because then they would occupy different physical locations and they would be further apart on average. So the repulsion between the electrons is going to be minimized. However, if they go into different orbitals, they have the same spin. They have spins in the same direction, they all become aligned. Now this kind of interaction in quantum mechanics is called an exchange interaction. Because for the electrons that are parallel to one another are just 5 dipoles that are all parallel to one another. This lowers the energy of the system. The details are beyond the scope of this course, but this is something that you generally remember as the LUMS rule in chemistry. So the first 5 electrons go into different orbitals because that lowers the electrostatic energy and it lowers the overall energy. And the electrons take up parallel spins. Now the 6th electron has no other option but to go into one of these orbitals. So it will come into one of these orbitals, but in doing so, it will have its spin anti-parallel to the one that's already in there because of Pauli's exclusion principle. No 2 electrons can be in the same orbital and have the same spin, because then all the quantum numbers will be exactly identical, and that's not allowed. 2 electrons cannot have the same quantum number. This is Pauli's exclusion principle. So now there are 6 electrons that have gone into the d orbital. Now look at these 4 unpaired electrons. These 4 unpaired electrons all have spins in the same direction. So their dipoles are all pointing in the same direction. These 4 electrons will give a net magnetic moment to the iron atom. So each iron atom will start behaving like a dipole. Okay? Each electron has a spin when measured along the z-axis of mu b. So these 4 electrons will have spins pointing in the same direction, and overall the atom, because of these unpaired electrons, will acquire a magnetic moment. So whenever I draw an iron atom, an isolated iron atom, I can associate with it a spin, a net magnetic moment. So each iron atom has now been magnetized. Now we're talking about magnetization at the atomic level. Because of the presence of these unpaired electrons, the iron atom has become magnetized. It acts like a dipole. Now if you look at the structure of iron, the big structure of iron, this was just an isolated atom. If you look at the big structure of iron, of an iron crystal, since it's a crystal, all of these atoms are arranged in a periodic fashion, in a regular fashion. So if I draw the structure of iron, I can draw a cube. On the corners of the cube exist iron atoms. And this is a perfect cube. So this spacing, if it's A, this spacing is also A. And there are iron atoms on the vertices of the cube. However, for iron, there is an additional iron atom at the center of the body of this cube, right in the middle, in the interior of this cube. So this kind of structure is called a body-centered cubic structure. So iron crystallizes in VCC form. It has a body-centered cubic structure. Now each one of these iron atoms is a dipole. It has a spin because of the unpaired electrons. Now because of the exchange interaction, all of these spins would like to point in the same direction, whatever that direction is. As a result, this cube has aligned magnetic dipoles. Now these dipoles will add up to give you a net magnetization, which is going to be the sum of the magnetic dipole moments of each one of these divided by the volume of this cube. So this entire cube will acquire a magnetization, some magnetization M. Alright? Okay. However, the iron, a crystal of iron does not comprise one cube. It has a huge number of cubes. So if you stack these cubes all together, into the front, into the back, left ways, sideways, everywhere, you can make a three-dimensional structure of iron. And that makes a single crystal of iron. Right? Now there's another property of crystals. Crystals are unlike liquids and gases. Liquids and gases are generally isotropic. So their properties do not depend upon the direction in which you're talking about. For example, this is air. If I'm moving in this direction, I feel some resistance to air. If I move in a normal direction, I feel some resistance. And that resistive force is going to be the same. No matter what direction do I move in, the viscous drag of air is going to remain constant. So liquids and gases are generally isotropic. Because, however, for crystals, obviously there are preferred directions. This direction along the edge, this direction along the edge, this direction along the edge, all of these directions no doubt are equivalent. There's no difference between this direction and moving in this direction because it's a three-dimensional structure. However, these directions are distinctly different from this direction that I've drawn, which is diagonal on a face. This journey, if I'm a small animal, an angstrom-sized animal, and I'm moving on an edge, I will see a surrounding, I will see a scenery in the surrounding. But if I move along the face diagonal, my scenery is going to change, the landscape is going to change. I'm going to encounter different number of atoms at different distances. If I'm moving along this distance, I'll encounter the neighboring atom after distance A. However, in this case, I'm going to encounter an atom at a distance of √2 times A. So my landscape is going to change. So different directions have different properties. So this face diagonal is going to be different from the edge diagonal. And if I draw a body diagonal, so if I connect this point to this point, then I'm drawing a diagonal to the body of the cube. This body diagonal is going to be different. If I draw another direction on the face, like this direction is going to be different from any other direction. So crystals generally are anisotropic. They are not isotropic, in other words. Now in the iron structure, it's a cubic structure. If the magnetization lies along an edge of the cube, then it's called an easy axis. So if I draw this cube again, and there are iron atoms here. Then this direction that I've drawn, which is totally equivalent to this direction, which is totally equivalent to this direction because it's a cube. The x, y, and z axes are totally equivalent, it's a cube. Then this axis, or these axes are called easy axes. Which means that if the magnetization lies along one of these axes, then the energy, the potential energy or the magnetic energy of this crystal is lowered. That's why this axis is called an easy axis. However, if the magnetization, for example, points in any other direction, suppose it points along the face diagonal. So if the magnetizations are pointing along face diagonals like this, then the energy of the system is going to be larger. There are certain preferred axes along which the magnetization would like to align itself because of the anisotropy of the crystal. So the axis that I've drawn, which is along a face diagonal, this is an example of a hard axis. Because if the magnetization would point along the hard axis, the energy of this crystal is going to be larger. So if you leave this crystal of iron on its own, spontaneously the magnetization would tend to align itself along an easy axis because that lowers the energy of the system. So this is a consequence of the fact that the properties of a crystal are different in different directions. Certain axes are preferred, certain are not preferred. Now with this basic understanding, we are actually in a position to understand why do we obtain a hysteresis curve like this. So let me draw this hysteresis curve again. This is H, this is M. By the way, I'm using a hysteresis curve, I'm jumping to conclusions. So this is a magnetization versus H curve. Suppose I'm at point A. At point A, the externally applied field is 0 and the magnetization is also 0. Now let's look at a piece of iron. Now I'm not talking about a single cube inside the crystal structure which is called a unit cell. This is a unit cell of iron. What I'm going to talk about is a crystal, is a big crystal of iron. Now this is a single crystal of iron. Just one crystal in which all the planes are parallel to one another. So, and now if I draw the magnetic moments of individual iron atoms, they are all aligned because of the exchange interaction. They are all aligned. And suppose this is say my easy axis as well. Alright, so they are all aligned and they're parallel with the easy axis. So since they're all aligned with one another, then there will be a net magnetization of this medium, M. You just take the vector sum of all of these magnetic moments and divide by the volume, get the magnetization. Now let's look at the energy of this system. This piece of iron is going to act like a magnet. It has some magnetization, so it's going to act like a giant dipole whose magnetization is M and whose magnetic moment is M times this volume. So this thing is going to act like a magnet, and if it acts like a magnet, it will produce a magnetic field. So if you draw the magnetic field around this crystal of iron, the field is going to come out like this because it's a giant dipole. It's going to come in like this. It's going to circulate around, and the field lines have to be closed. So there is going to be a field, and that field pattern is going to look something like this. So even though inside the crystal the energy is lowered because everything is along the easy axis, the magnetization is along the easy axis, there exists a field outside this piece of crystal. Now every field, whether it's an electric field or it's a magnetic field, carries energy. For example, we discussed in detail electric fields. If we have an electric field and we place a test charge, it can accelerate inside the field. it will have a certain potential energy. So this system will have a certain potential energy, and that potential energy is stored inside the field. Bigger the field, bigger will be the energy. That's why a magnet can lift objects. The magnet can lift objects, which means that the field has energy in it. So now this single piece of iron, this crystal of iron, has produced a magnetic field. So even though inside the magnet, the magnetization is in a direction so that the crystalline energy is lower, because everything is along the easy axis, there is a field outside, in space, outside the magnet, which raises the energy of the system. So the energy is not really small in this case because of the existence of a field outside this piece of iron. So what's going to happen is, this system will tend to lower the energy. And how can it lower the energy? It can lower the energy by having no external field. Okay. Now this is magnetism combined with thermodynamics. We want the energy of the system to be lowered. The energy of this crystal on its own is lower, but the existence of the field that it produces raises the energy once again. This kind of energy, which is outside the magnet, is called the magnetostatic energy. So what's going to happen is that if this single crystal of iron partitions itself into two equal halves, all of the magnetic moments are aligned in one of the halves, and all of them are aligned along the easy axis. But in the other half, they are all aligned within the half, within this region, within this sector, but they are anti-parallel to the spins in the other sector. So in this region, the spins are parallel, and in this region the spins are parallel, but in between these sectors the spins are all anti-parallel. So what this means is that inside this region, let me draw another figure. So this thing is totally equivalent to what I'm going to draw here. I have two sectors inside this crystal. In each sector, the magnetization in this sector is pointing in the upward direction, M1, and in this sector it's pointing in the downward direction, M2. The spins are all parallel, no doubt, inside this sector, and they're all parallel inside this sector, so they will add up cumulatively to give you a net magnetization here and a net magnetization here. So this sector is called a domain. So this single crystal has subdivided itself spontaneously into two domains. Now how does this help? Now each one of these domains will act like a dipole. Right? It has a magnetization. So means intuitively at the back of your mind you can consider that there is a south pole here and a north pole here. And there is a south pole here and a north pole here. This is what it represents in an equivalent fashion. Now if you draw the magnetic field produced due to this arrangement, first of all, is this magnetization along an easy axis? Yes. Is this along an easy axis? Yes, both of these magnetizations are along easy axis. Now if you draw the magnetic field lines due to this two-domain configuration, field lines will come out of the north pole and go into the south pole. They will come out of the north pole and go out into the south pole. And they will be continuous. They have to be continuous because of Gauss's law of magnetism. So field lines will have a configuration like this. So now as compared to this configuration, no doubt there is fringing field. There is field that is outside this crystal of iron, but the field strength outside is much smaller. So now this configuration has lowered the magnetostatic energy as well because the field is smaller outside. So this is a preferred, energetically preferred situation over this situation. because the magnetostatic energy is also lowered, and the crystalline energy, the energy inside the magnetic crystal, is also lowered. No doubt there is some fringing field. However, this fringing field can also be suppressed. By the way, what's the magnetization of this entire volume of iron? 0. Even though each domain may have a large magnetization, still this piece of iron is unmagnetized on a whole. Being unmagnetized on a whole doesn't mean that the individual domains are unmagnetized. You can have domains pointing in random directions. Each one of them carries a magnetization, but the overall magnetization is 0. Now this fringe field can be suppressed totally, and that can be suppressed by having a microstructure like this. So now if I draw the magnetizations, so if I have a microstructure like this, in which this is the so-called south pole, so-called north pole, so-called south, north, south, north, south, north, then this kind of structure will not have any magnetic field that leaks outside the magnet, and its magnetization is also 0. So now 4 domains have been created inside a single crystal of iron. And the domains that are drawn at the top, these domains are generally called the closure domains, because they close the flux. So this is an energetically an even more favorable situation. Now suppose what we have is a single crystal of iron that has been broken into 4 domains. Remember that you can have more domains inside this material as well. And you can have the suppression of the external magnetic field even more pronounced. For example, you can have a structure like this. Alright, so you can even have a random arrangement of domains in real structures, and these domains can actually be imaged by techniques that we follow in our laboratory, in my research as well. So you can image these domains. Anyway, this configuration, suppose this configuration corresponds to point A of this curve. Point A. This is where the magnetization is 0, and H is also 0. Now we're going to increase an external source. We're going to apply an external field which corresponds to magnetizing force. Okay. This field is going to have a certain direction. Now I place this medium inside an external field, and I would like to see how the magnetization changes. After all, that's what this curve actually means. I would like to change the field, applied field, and see how the magnetization changes. Now what's going to happen? Remember that this is an easy axis. Okay. Now what I would like to do, I would like to find out what's going to happen at another point B, say point B. There will be lots of sketches today. Suppose my applied field H is along this direction. It's not along an easy axis. So my applied field is H. And since I'm talking about fields, I'd just like to put in a mu naught here, because this will have dimensions of a magnetic field. So this is my external stimulus, mu naught H, or H. And this is the direction of the field, and this object with this domain structure has been placed inside this field. Now this field is obviously not in, the easy axis, it's not along the easy axis. And these magnetizations don't want to change their orientation. They don't want to go away from the z-axis, because then the energy of the system is going to raise. However, it is being pressurized by the external field to readjust itself. Because what's going to happen, if this is an external field and this is a magnetization, suppose this is my applied field, it's in this direction. I'm drawing a small figure here. This is my external field, mu naught H. This is my magnetization. So when a magnetization or a magnetic moment is inside a field, what's going to happen? A torque is going to act, mu cross B. So the torque is going to act, and this magnetization will tend to shift itself. It will tend to reorient itself. But then it has to move away from the easy axis, because if it goes away from this easy axis, the energy of the system is going to go up. So what's going to happen is that this magnet, this piece of iron, tries to resist external pressures, and it would like to remain along the easy axis. So what's going to happen is that this particular domain, the sizes of these domains is going to change. Now this magnetic moment has a lower energy as compared to this magnetic moment if this is the applied field. Because we know that the energy is given by minus mu dotted with B. So whenever mu is parallel to B, when theta is close to 0, the energy is lowered. So for this particular configuration, this is theta, it's small. For this particular configuration, theta is large. So this has a higher energy in the external field. This domain has a higher energy as compared to this energy, this domain. Because this domain has its magnetization somewhat parallel to the applied field. This domain has a magnetization somewhat anti-parallel to the applied field. So this domain will like to grow. This domain will like to increase its size, and it will try to eat up the smaller domain. The total volume is fixed. So what's going to happen is that the left domain is going to grow in size, like this. And the right domain is going to shrink slightly. Can you repeat this argument? Now this is a magnetization, this is the applied field inside this domain. Now this magnetization will have a lower potential energy inside this field, because whenever a dipole is parallel to the field, the energy is lowered because of this. Now here the field is like this, the dipole is like this, so they are almost parallel to one another. This is going to be a high energy configuration because the moment is pointing down and the field is pointing generally upwards. So this is a lower energy configuration. So if this microstructure has to readjust itself without changing the orientation of the magnetization, because they are along the easy axis, the only possible way it can do is that this domain grows in size and this domain shrinks in size. Now what's going to happen is, since this domain has grown in size, this magnetization goes up. This magnetization goes, the magnetization remains the same, but the magnetic moment of this domain goes up, because magnetization is moment per unit volume. Since this volume is larger, the magnetic moment here is going to grow big, the moment here is going to be smaller, and still you will have these closure domains. So now this entire medium will have a net magnetization, will have a net magnetic moment in it. So remember, I'm talking about magnetic moments. This has a magnetic, this is an unmagnetized medium because the magnetization is really zero. Here the magnetization is non-zero because this magnetic moment is larger. So this M is going to be non-zero. And this is the new domain structure. So one domain which has its magnetization along an easy axis and parallel to the field grows at the expense of another domain in which the moment is lying anti-parallel to the field. Okay. That lowers the energy of the system, because remember, you're pumping in energy by applying an external field. That external field will necessarily raise the energy of the system. But what is the minimum energy configuration within the given scenario? Within the given scenario, what's going to happen is one of these domains, which has the moments aligned parallel, somewhat parallel to the applied field, is going to grow larger in size. And magnetization is then going to be non-zero, so you get some magnetization here. Now this effect is going to increase. If you apply larger and larger fields, this domain is going to get larger and larger and larger. And finally, what's going to happen is that it's going to engulf this smaller region. This domain is going to vanish totally. So at some point, if you increase the field beyond bounds, at some point C, what's going to happen is that the entire medium will become a single domain. Because this domain has shrunk, it has vanished, it has been engulfed by the expanding, hungry domain. It just scavenges the smaller domain, just goes away. Because this domain has grown in so large that it has overcome the entire single crystal. So now the single crystal comprises one domain. And you get a situation like this. And this is point C, this is point B, this is point C. This is now a single domain. And remember, you have now applied a large magnetic field. Mu naught H is large. It is sufficiently large that this domain has grown in size to the extent that it has scavenged all other domains inside this crystal. Now you get a single crystal which is also single domain. In fact, nanoparticles that you make in the chemistry lab, generally if they are smaller than 30 or 40 nanometers, they are always single domain particles. Each nanoparticle is just one domain. In fact, this effect is also called super paramagnetism for the interested souls. Alright, now you have a situation in which you have applied a field and the magnetization is still pointing in an easy axis. Now the magnetization of this medium, can it be larger than the magnetization that we have here? Can it be any larger? This means that inside this crystal, all of the tiny domains, all of the tiny dipoles, they are all aligned with one another. Can you have a better alignment than this?
So if all the tiny packets align with the hard axis that they align with the external field.
But then the magnetization is going to be the same. So this is the extremum. You cannot have a bigger magnetization than this because all the dipoles, they are all aligned with one another. You cannot have a better magnetization, a stronger magnetization. You've hit the limit. So this means that the magnetization has now saturated. You cannot increase the magnetization beyond this value. Okay? So now this curve has now reached the saturation point. So even if you increase the field now, the magnetization is not going to go up because the structure is now a single domain and all the dipoles have aligned with one another. Now what happens if you increase the field further? Now the pressure is so immense on this magnetic material that this single domain has no option but to shift away from its easy axis. Okay? So now what's going to happen is a torque will act on this magnetization and it will cause this magnetization to reorient itself and finally become parallel with the external field. So now on top of this, if I increase the external field even further, remember I'm not changing the direction of the external field, I'm just ramping it up in magnitude. So my field is, now I'm at point D and here is point E. This is point D, this is point E. E is a larger field, an even larger field. Now the magnetization has no option but to reorient itself away from the easy axis. The magnetization is pointing in this direction, there's a torque acting on this magnetization on this dipole, that torque has direction mu cross B. It twists in the clockwise fashion, so it tries to become parallel to the external field. This is how a dipole changes. So what's going to happen is that this magnetization vector is now going to, this is the easy axis, it's now going to shift away from the easy axis. It's going to shift in the clockwise fashion. And you get the point D. But this magnetization is the same in magnitude as this magnetization, because there is no better alignment that can be achieved. If you increase the field further, eventually a situation is going to arise when the magnetization will now be pointing parallel to the applied field, albeit it's not in the easy axis, it's in some hard axis. Okay? So this is the scenario that we have at E here. Now the interesting point is what happens when we now lower the field. Which means that we would now like to go back from H in the reverse direction. We would like to lower this field slowly. So the observation says that this curve is not going to take its original path. It's going to come back down some other path. Hence this curve is called a hysteresis curve. Because the forward path is not the same as the backward path, it's much like an elastic. Now what's going to happen if this field, if we reverse this field, reversing the field actually means that we are lowering the magnitude of this field. So this field is now lower in magnitude, but it's pointing in the same direction as this. We're not changing the direction of externally applied field G.
Going negative over there.
नहीं यहाँ पर देखो अभी मैं इस वेन को H is positive here, which means that I've applied the external field in a certain direction. Now I'm just lowering the magnitude of this field. Alright? ठीक है? I'm not reversing the direction. I can reverse the direction if we go into this quadrant. Now what I'm doing, I'm just lowering this field back again. Now what's going to happen? There is no reason why this magnetization will shift back to its original position because there is no torque acting on it. It has been pinned in this direction. So what's going to happen now is that domains might start to form. The domains that had formed here will actually start reappearing. Okay. Excuse me. Just this point. Alright, so what's going to happen here? Look at this configuration. This magnetization is along a hard axis and it's acting like a big dipole, so it's going to produce a magnetic field. So there's going to be a magnetic field outside this particular region, like this. Okay? Which means that the magnetostatic energy of this configuration is large. But the system would like to lower its energy. So these new domains are going to be formed. When these domains are going to be formed, it will of course have these closure domains, and these magnetostatic energy is going to decrease. So new domains are going to be formed and they will have the magnetization pointing in these directions. So the magnetization points like this. A new domain is going to be formed whose magnetization is going to point like this. Still this medium has some net magnetization. Is not zero. So now you generally lower this field. You keep on lowering this field, this domain can actually grow. Because this has favorable energy, this has unfavorable energy. But you would like to lower the overall magnetostatic energy. So the overall magnetostatic energy will be lowered when actually this domain is roughly of the same size as of this domain, because they have magnetization in the opposite direction. That will not produce any magnetostatic energy. So what's going to happen is that as you lower this field, eventually this domain is going to grow larger in size and this domain is going to grow smaller in size. So eventually you reach this point, say F. At this point there is still some net magnetization, and in the meantime, since the field is now much smaller, this magnetization can also snap back to its easy axis. So in the meantime, what's going to happen at some intermediate point is, at some point F, you will have a structure like this. Still the domains have actually not grown equal in size. So what in the reverse direction, what the magnetization and the domains have to do? They have to do two things. First of all, they have to go back to the easy axis. Second, the domain sizes have to readjust so that the overall magnetization of this medium turns out to be zero. However, in the reverse path, when this sample reaches the point F, this regrowth of domains has indeed taken place, and these magnetizations tend to shift back to the easy axis, but they do not shift back completely up to the point F. This domain is still smaller than this domain. This is a larger domain than this domain. So at point F, still there will be some remnant magnetization. The magnetization has not gone to zero. So you achieve point F. If you would like the magnetization to really go back to zero, what you require is that this domain has grown to the same size as the left domain. and the net magnetization would then go back to 0, and the magnetizations in each one of these axes is now in the along the easy axis. So at this point G, which requires the field to go in the opposite direction. So you apply on top of this domain structure a field in the opposite direction. You start applying a field in the opposite direction. This would ensure that you get back a configuration like this. And that ensures that at point G, the magnetization has gone back to 0. So this is a complete description of a magnetization versus H loop for a ferromagnetic material. Now you can have different kinds of ferromagnetic materials. Okay, one interesting observation is the following. If you have a domain here and a domain here, this lowers the energy of the system. Okay? Because the magnetostatic energy is lower. Alright, we know that. So why doesn't a material like iron always spontaneously split up into many small domains? Because that's going to lower the magnetostatic energy. That's the question. The question is that this configuration has a lower energy than this configuration. Why? Because the magnetostatic energy is lower. Each one of these domain magnetization is pointing along an easy axis, and the field outside the material is smaller. The magnetostatic energy is smaller. So this is a better configuration. It's smaller in energy. I can even have a configuration that is something like this. I can have 4 domains. This will even have a smaller magnetostatic energy. So there will be some fringe field in this particular case. But the fringe field here is going to be even smaller. And in fact, on top of this, if you apply closure domains, so if you have a configuration like this, the fringe field is even going to be smaller. So why doesn't a piece of iron spontaneously always break down into smaller and smaller domains? The reason is, can you come up with the reason? It's based upon thermodynamics and the concept of this anisotropy that I've talked about. Just imagine what's going to happen in this region. This is the boundary between 2 domains. So if I zoom in onto this region, I'm drawing a boundary between 2 domains. In this domain, the magnetization is in the upward direction, and in this domain, the magnetization is in the downward direction. And this boundary between the 2 domains is called a domain wall. Now everything is continuous. This is continuous matter. So this domain wall will have a certain thickness. When we studied junctions, PN junctions, the depletion width was a few tens of angstroms or a few hundreds of angstroms. So everything is continuous inside matter. The wall between these 2 domains will have a certain atomic level thickness. It might comprise of 100 atoms. It might comprise of 1,000 atoms, iron atoms. And they will have spins pointing in some direction. It's not possible that the magnetization points in one direction in one domain and immediately at the level of one atom just points in the opposite direction. Because that will make the spins in one domain up and the spins in the other domain down, and this energy is large because of the exchange interaction. Because for iron atoms you would like to keep the spins parallel to one another. So this transition has to be smooth. We are making a transition from up spins, up magnetization to down magnetization. This transition has to be smooth because otherwise the energy will be really large at this interface, because then you have oppositely pointing magnetization, oppositely pointing spins. That's not allowed. You would like to have iron atoms all pointing in the same direction. So what happens is that this domain wall has a certain finite thickness, a few hundred angstroms perhaps. And the iron atoms inside this wall, they gradually shift their magnetization. So the iron atoms here will have the magnetizations or spins pointing up, here they will be pointing down, and in between there will be a gradual transition of the magnetic moments of the spins. This means that the energy, the exchange energy between two spins is not as drastically as large as you would have if the spins were pointing in opposite directions. So this domain wall has a finite thickness. But look inside the domain wall, when you have a transition from a magnetization along an easy axis to a magnetization along an easy axis, although in opposite directions, inside the domain wall you have spins that are pointing along the hard axis. And that increases the energy. So the argument is that if you would like to have multiple domains, that is favorable from the point of view of lowering the magnetostatic energy, but that increases the energy inside the crystal because you have more domain walls now. When you have more domain walls, you have more spins inside this crystal which are pointing in the wrong direction, which are pointing in the hard axis. So there is a seesaw effect. There is a trade-off that happens between the lowering of the magnetostatic energy and the increase in energy due to the formation of domain walls. Domain walls means energy goes up. Domain walls means that domains are higher in number, so magnetostatic energy goes down. So domain formation lowers the magnetostatic energy but ramps up or increases the domain wall energy. So a compromise has to be reached. And domain wall formation or domain formation will stop, cease whenever the two energies balance out one another, whenever there is a break-even effect. So the concept of domain formation and energy and magnetism are intimately related. And you can have different kinds of hysteresis curves. For example, if you would like a permanent magnet, you would like to have a hysteresis curve like this, in which this remnant magnetization, this point, the remnant magnetization, the magnetization that remains whenever H has gone to 0 is large, because you would like to use this as a permanent magnet which has a magnetization even in the absence of an external field, so that you can use this magnet as a permanent magnet. So for certain materials you would like a hysteresis curve like this which have a large remnant magnetization. The coercivity, by the way, is also large here. For soft materials, for example the materials that you use in transformers, you don't want the magnetization to remain stuck inside the medium. You would like the field to reverse because you are applying an AC current in transformer, so H is actually reversing its direction, and you would like the magnetization to reverse in tandem with the applied field. So you do not want any remnant magnetization. So what you really want is a loop that resembles this. You want remnant magnetizations that are really small. But you would like to have strong magnetic fields or strong magnetization. So you would like to have strong MSs. This MS means saturation magnetization. So if you want high frequency applications, or you would like to create fluxes that induce EMFs in other coils, you would like to have a curve like this, which is characteristic of a soft ferromagnetic material. This is a characteristic of a hard magnetic material. A hard magnetic material may also have a large coercivity. You would like coercivities to be large for memory elements, because if you store something in this particular state, in the positive magnetization state, this is one bit of information, 1, you call it logical 1. You do not want this logical 1 to go to 0 on its own with the help of some small coercive fields. Here, if you look at the magnetization here, it can easily slip to this magnetization by the application of a small field in the reverse direction. So because the coercivity here is small. But you would like to have large coercivities for memory elements which store information in one of these magnetization states. So this magnetization really means that the magnetization is in one direction. This is a negative magnetization, which means that the net dipole moment is in the opposite direction. So these are two logical states of a memory element, of a transistor, of a flip-flop, or a bit in the register of the computer memory. So you will have to engineer different kinds of hysteresis loops to obtain desired behaviors. The last thing I would like to talk about in the last 5 minutes is quite interesting. And then I would like to show you a demonstration. What I would like to talk about are diamagnets. Now diamagnets have a negative magnetic susceptibility, which means that M equals chi H, and this is M is parallel to negative H, because this is negative. So if you apply an H field in this direction and you place a magnetic medium which is diamagnetic inside this field, the magnetization is going to point in the opposite direction. And bigger this H, bigger will be this M. So the net field inside this medium, B, is going to be smaller than mu naught H. You increase H, the field inside this medium gets smaller and smaller and smaller. Which really means that field does not like to go inside diamagnetic materials. This is what the meaning is. You increase the applied field, the field inside the medium goes down. It resists the applied field. Field is expelled from this medium. Okay, this is what a diamagnetic medium really is. And this is described by Lenz's law. I'll explain that in the next week. Now, this guy is really small for diamagnets. If you look at the values here, the absolute value is really small. So this effect is really small. That's why this observer is hardly noticeable in our daily lives. However, there is a certain class of materials that are called superconductors, for which this effect can be really large. In fact, for a particular kind of superconductors, which are type 1 superconductors, this effect can reach its extremum. And what's the extreme value X guy can take? What's the extreme value it can take? -1. That's an extreme value. Now, if B equals inside the medium mu H plus mu naught M, mu naught H plus mu naught, this M is chi H, mu naught 1 plus chi H. If this guy is generally really small, so the diamagnetic effect is really small. However, if this guy can be ramped up to large negative values, such that this guy becomes equal to -1, then that material is called superconductor. There are other properties of superconductor, but this is a magnetic property of a superconductor. For a superconductor, chi is at its extremum value, which is -1, which means that this thing is 0, which means that the field inside a superconductor is always 0. So if you have a magnetic field produced somehow, say by an external magnet, North Pole, South Pole, and then inside this field you place a superconductor. Now this field has to go outside the superconductor. It's expelled from the superconductor. it cannot penetrate inside the superconductor, because the magnetization that is created inside the superconductor M is equal to H, but in the opposite direction that has been created by this external field, so that the net field inside the superconductor is 0. This means that if this is, you consider this to be a magnet. This magnet has a north pole here and a south pole, so its dipole is pointing in this direction. If this were a magnet, this superconductor is considered to be a dipole in itself. Look at the direction of its magnetization. The south pole is here and the north pole is here. Now you have two north poles facing one another. And if you look at the force that acts on this dipole, because of this field, the force is in the upward direction. This superconductor will be repelled by the magnet. And it can be repelled in such a fashion that the repulsive force is greater than the force of gravity, so it starts levitating. This is called the Meissner effect. Now I have a demonstration for you that actually shows this effect. But what I'm going to do now is I'm going to place my superconductor here. This is my superconductor. It's a heavy material, so I placed it at the bottom and I place a small disc magnet I hover it above the superconductor. But the point is that a material can only become superconductor under certain conditions. And the conditions that I've chosen for a material is that I need really low temperatures. So I put this superconductor inside liquid nitrogen. The superconductor that I'm using is yttrium barium copper oxide. It's a compound of yttrium, barium, copper and oxygen that we made in the laboratory in a particular stoichiometric ratio 1 to 2 to 3 with oxygen. It's a type 2 superconductor and it's only superconducting below about 120 kelvins. Above 120 kelvins it's non-superconductor, it's a normal material. So it becomes a perfect diamagnet when I immerse this inside liquid nitrogen. So what I'm going to do now is I'm going to show you a demonstration. It's going to take 5 minutes. Slightly tricky demonstration. So here I have liquid nitrogen. So I'm going to pour some liquid nitrogen into this thermos flask. Alright, so what I have here is what I have here is I have a petri dish. Inside this dish I have a superconducting pellet and I have these tiny magnets on top. This is a tiny magnet. I'm trying to levitate this magnet on a superconductor. Currently, if the video camera turns on, you'll see that this magnet is perched on the superconductor. Because the superconductor is not a superconductor at this instance because it's hot, it's at room temperature. Okay, Ali, please put it. बिल्कुल zoom in करना पड़ेगा. ठीक है, थोड़ा सा. Alright, so at the bottom here, this is just a styrofoam dish. This is a superconductor. This is a superconducting disk, and this is a normal magnet, a ferromagnet, which is a permanent magnet. It's a strong magnet. Okay. Now what I would like to do, I would like to cool this superconductor. so that it comes below its transition temperature, which is about 120 kelvins. I would like to make the temperature go to 77 kelvins. Okay, when this cools, I would expect that this magnet is going to levitate. I could have done the reverse. I could have a magnet at the bottom and a superconductor that is levitating. But here I chose to levitate the magnet. That's immaterial. So what I'm going to do now, I'm going to turn off the light slightly. Let's see. Let's see if this magnet levitates. You notice that it's already lifting one of its faces, one of its edges. And it's levitating. थोड़ा सा फोकस करो, नजर नहीं आ रहा सही से. थोड़ा जूम कर सकते. बस. Here you go. थोड़ा सा जूम कर. Now it's purged back. Let me redo this experiment. Just a minute. Yeah. उधर से थोड़ा सा और जूम कर. Here you see this magnet is in almost midair, it's just levitating. it's not actually just barely touching the surface. You see? Now you can see this effect quite vividly. It's hanging in midair. It's not touching the superconductor. And as this superconductor warms down, it comes back. It just perches down. Let me repeat this one. It's worth it actually. Just repeat it once more. It's quite a subtle effect because it's difficult to get the conditions right. Here you see, it's in midair. It's levitating. Okay? Levitating. Okay? Alright, now it's warm back. Alright, so this effect actually, you've seen this. It's actually more pronounced when you look at it from the naked eye close enough. Alright, so this is the diamagnetic, this is the extreme diamagnetic effect. You can levitate magnets, superconductors. Best of luck for the quiz tomorrow.